Welcome to Lecture 7b, entitled Tangential Plane and Linear Approximation to Curved Surfaces. The material for this lecture comes from section 15.6 of the text, including some supplementary material provided in this lecture. The objectives are estimating how the output value of a multivariable function varies with respect to small changes of variables about a reference position or point in absolute and per unit terms. The concepts and visualization skills obtained through this lecture include the multivariable Taylor series expansion, the derivation of a tangential plane from a Taylor series expansion, the Hessian matrix, which is a specific property which is tied to determining the maxima and minima when you're dealing with multivariable functions, the derivation of a tangential plane using the normal to the surface. It's an alternate approach in terms of deriving the tangential plane. And lastly, per unit calculations, which we also call sensitivity analysis. Just a reminder, we briefly discussed tangential planes when we introduced multivariable differentiability in Lecture 4b. As usual, the second slide is a summary of the contents to follow. And so here we basically itemize in terms of 6 different items. Items 1 and 2 and 3 are not in the textbook. These are supplementary. It just gives you an alternate approach in terms of how to look at the subject of tangential planes. And so this has been basically included as well. All right, so just a quick review in terms of a Taylor series expansion of a function describing a curved line. So what we're trying to do is approximate a curved line at a given point. So this would be some position xy, which is AB on the xy plane. And so the Taylor expansion would be that f of x is f of a plus the derivative of f with respect to x evaluated x equals a times x minus a. And if we carry out this to higher order terms, then we'll have the next most significant term will be the second derivative with respect to x multiplied by 1/2 x minus a squared, and so on. So the critical points of a function y of x are determined by setting df dx equals 0 and solving the resultant equation for x. The second derivative test is used to determine if a critical point is a local min, a local max, or an inflection point. Of course, this assumes that the second derivative exists. If it doesn't, then you would have to basically go to higher order derivatives to determine if there's a max or a min. So the first order approximation to the curved line would be taking the Taylor series expansion and only redating the linear terms. So that means y is equal to f of a plus df dx evaluated at x equals a times x minus a. The picture on the right basically shows how we establish the tangent line, which is in fact the red line, which represents the first order approximation. And so in the limit, we basically are just looking at the behavior of the curved line at the point P for very small changes taking place, which means it is a straight line, and that straight line is in fact described by the equation at the bottom left. All right, so now let's basically extend the notion of Taylor series expansion of a function to a curved surface. In this case, the points of interest would be some x, y, z is equal to a, b, c. So that would be in a three-dimensional space. So in this case, if we're interested in looking at the nature of the function about a point, that is at a, b, c, we would expand it in a similar fashion as we did for the case of one variable. But now we have more derivatives to consider. We have all these partial derivatives. And so in this case, basically, when you expand to first order, you have a partial f with respect to x times x minus a and a partial f with respect to y times y minus b. When you expand to second order, that means you have to take second derivatives. So now consider all the possible combinations in terms of how you can take second derivatives. So you can take a second derivative of x twice, you can take a second derivative of y twice, and you can take mixes. So you could take derivative with respect to y followed by derivative with respect to x, or the other way around. We mentioned in an earlier lecture that second derivative with respect to y and x is equivalent to second derivative with respect to x followed by y if certain conditions on the function basically are maintained, particularly continuity. And so that means that in effect, the two terms can be grouped together and added because they're exactly the same. In fact, you'll notice here, what is the difference between this term and this term? No difference, other than the ordering of the multiplication of these two here. So it's y minus b times x minus a, but that's equivalent essentially to the product of x minus a times y minus b. So you have your first order terms, which are these. This is a 0th order term, and these are all second order terms. All right, now it's useful to take what we've just written and let's put this in matrix form, because we mentioned in a much earlier lecture that in fact you can take dot products, and write them out basically as vectors, or you can basically write them in matrix form. So if you look at this expression now, you'll notice I've written it out as this is a constant c. This constant c mirrors the value of the function evaluated at a and b. And so this is now the dot product between a vector and another vector. The vector d is going to be composed of an x component of x minus a and a y component of y minus b. And the gradient we know has this form. If I take a row vector, okay, if I take this as a vector, and I take this as a dot product, this is a vector and a vector, then this basically will give you a scalar, which is equivalent to the expression we had on the previous page. Now in this case, the second order term, we can basically use this expression to get the second order terms on the previous page. However, we have to make a slight change. And if you'll notice here, for instance, I've got star, which basically is meant to mean multiplication. And so we're basically now looking this now in matrix form. So D would be basically a row, and D transpose would be a column. And H would be basically a matrix, which includes all those partial derivatives that we looked at in the previous slide. So there's the second derivative with respect to x, xy, yx, and a derivative with respect to y taken twice. This thing is called the Hessian matrix. Now, as an exercise, if I take D, which is this, times this matrix, times D transpose, I'll get the same expression as you saw on the previous page. So this is in a much more compact form, and it's much easier to work with in many cases. So what about the critical points in this case? In other words, where will I expect to see local min, local max, and something I called a saddle point, which is the 2D equivalent of an inflection point in 1D? Well, we basically, by setting these partial derivatives to 0 and solving the resulting equations, we can determine the critical points. And the second derivative test is used to determine if the given critical point is a local min or a local max or a saddle point, assuming the second derivative test gives conclusive results. The second derivative test is buried in the details of the Hessian matrix. It is a symmetric matrix, right? Symmetric meaning if you look at this side and this side are equivalent to each other. So this is a symmetric matrix. But it's not discussed in this course, but is the subject of section 15.7 of the textbook. It's no longer part of the course because we introduced reading week, and that meant something had to go. And the textbook doesn't really do justice to the topic. It's best treated on its own in a more expanded fashion. And so basically that's why this was left out. So you don't need to know anything about taking second derivative tests. It's just here for your interest. All right, so let's basically look at taking to first order. So we take the previous results and look at first order. And so we only retain these two terms here. All right. So this is C, that's the value of Z that we're interested in, A and B. And so this is basically the first order expansion. All right, now we're going to basically wanting to determine what the tangential plane is. And since it's linear in X and Y, you would assume this starts to look or has a resemblance of a tangential plane. So what we're going to do is rearrange terms. We're going to bring the C over to this side. That's this, what you see here, and we're left with just this expression. And now what we do is we take all things which are of a constant nature, which means the C's, the A's, and B's, and bring them over to the right-hand side, which is what you see here. And everything involving the variables, X and Y, is on this side. So we have a Z, we have an X, and we have a Y. If you look at this, you'll notice that all the items marked in yellow These are constants because we're going to evaluate this at A and B, at A and B, at A and B, and A and B, and A, B, and C's are all constant. So what is this? This is the equation of a plane. This is the equation of the tangent plane at the point A, B, C. All right, so we are now in a position to derive the equation of a tangential plane. And we're doing it by basically making use of the Taylor series expansion of a function that describes the curved surface to first order at a given point, namely x, y, z evaluated a, b, c. And so if we look at the first order expansion, multivariable Taylor series expansion to first order, then we end up with z equals the function itself, which is equal to, in terms of first order expansion, constant c, which is this, the z component, plus the partial derivative with respect to x evaluated at x equals a, y equals b, x minus a, plus the partial derivative with respect to y, also evaluated at x equals a, y minus b times y minus b. So this is our starting point. So next step is to rearrange the terms. We're just going to bring the c over to the left side, and so we end up with the expression shown here. And then after doing some further rearranging, so effectively what we do is place all variables, that's z, x, y, on one side, on the left-hand side, and bring everything else over to the right side. We end up with this expression here. And so on this side, we have something times x, something times y minus z. The things marked in yellow are all basic pre-calculated constants. So everything on the right is a constant times x plus constant times y minus z. This is, by definition, the equation of a plane. All right, so let's look at an alternate method for determining the equation of the tangent plane, but using the normal to the curved surface. So I've got two pictures here. The first picture indicates that the gradient of a function, the implicit function, is normal to the surface at a given point. At the same time, we can basically draw a curve that is sitting on the curved surface, and that curve basically, each point along that curve can be described by a position vector, and so in this case it's a parametrized form, and so this would trace out every point along the green line as t is advanced. If we now take the derivative of this with respect to variable t, that becomes the tangent vector at every point on this curved line. So if you look at this tangent vector, right, this basically will change its direction as you move along the curve. All right, let's look or consider another curved line that lies on the surface. In fact, multiple versions of curved lines is shown over here. So again, we can compute the tangent vector for each one of these curved lines. And it turns out if you were to plot these tangent vectors, they'd all lie on the same plane. And this plane basically is the one that's defined in terms of the color purple, right? So they all lie in the plane. The other thing is, if we want this to be a plane, then what we would like to make sure is that any of these vectors, for instance, this vector here will have a position at some point here, and relative position of p naught here. The difference there will produce a vector. And so by treating the endpoints as being variables, that's some variable x, y, and z, and this, of course, is a given value of, say, a, b, c, then the dot product between these, any one of these vectors and the gradient must be equal to 0 to enforce the condition that we, in fact, that we have a tangential plane. And so mathematically speaking, that is the next step that we will take. All right, so here are basically the details. So we're going to consider the position x, y, z at any point on the tangent plane and create the vector between this point and the point ABC on the surface. So that's our reference point on the surface. Then if we take the gradient of the function, the implicit function fx, y, z, dot product with the difference, the x, y's, and z coordinates, so these are basically arbitrary vectors. In order for this condition be such that these would represent a tangential plane, the dot product between these two must be equal to 0. All right, the gradient vector, you can basically spell it out in detail. This is a partial of f with respect to x, evaluated a, b, and c. Similarly for y, partial for y, similar here for partial for z. Again, evaluated x equals a, y equals b, and z equals c. All right, now what we can also do is we can write the implicit equation in an explicit form. So for instance, if z is equal to f of xy, right, and we subtract z away from fxy, then this expression equals 0. But this is another way, basically, of writing it in this form. So if we take these expressions and apply them directly to this expression on the right, then we end up with df by dx, evaluated x equals a, y equals b, z equals c, is just f partial x, x equals a, y equals b. Similarly, f for y becomes f partial y, x equals a, y equals b. You can see that immediately from that is that x, the derivatives with respect to x and y operate on this one. This plays no role. And the last item, df by dz, only operates on this one. So derivative of minus z just becomes minus 1. All right, so now what we do is we make the substitutions of these expressions into the expression that we had previously, which is up here, right, and carry out through the calculations, right? And if you manipulate things around so that all things which are involving variables are on the left side and everything involving constants on the other side, then we end up with this expression that right here. But this is the equation of plane using the explicit representation. So essentially, we basically gotten to the same result as what we derived on page 13. So let's work through an example here. Determine the equation of the tangent plane at the position pi over 4, 2, 1 on the surface z equals sine xy. And so what we'll do is take the partial of f with respect to x, evaluate x equals a, y equals b on this function here. If so, we get b cosine ab. We'll put in the values of a and b later, but for now we just put it sort of in a very generalized form. For partial f with respect to y, we end up with this expression. And now basically we make the substitutions in for the individual terms, this one, and this one, and on this right-hand side, this one and this one. It turns out that when you put a and b in, you'll get a pi over 2 here and a pi over 2 here. So both of these terms make 0 contribution. And so the only ones that are left basically will be the value of c, which is 1, and minus z. Right, so you have a minus z is equal to a minus 1, hence z is equal to 1. All right, so then let's look at a sensitivity analysis, again starting with the Taylor series expansion, the first order. What we're doing here now is bringing c to the other side, so everything is in terms of differences. So z minus c, x minus a, and y minus b. And now what we're going to do is let delta z be z minus c, delta x be x minus a, and delta y equal y minus b. And in a more compact form, we can say that small changes in z that occur as a result of small changes in x and small changes in y can be computed by basically this expression shown here. So we have to take the partial of f with respect to x, partial of f with respect to y, evaluate at the point of interest, from which we can determine for a given change in x and change in y, what the change in z will be. All right. Other thing that comes in handy then is a per unit analysis, sensitivity analysis. So what's the difference here? Well, what we will do is we'll take the expression from the previous slide, and we're going to divide through by z on both sides. So you have dz over z, you have a z showing up here, and you have a z showing up here. Now, the dx, basically we want to make it per unit. So what we do is you divide it by x and multiply it by x. So effectively nothing has changed. Y, we divide by y and multiply by y. So nothing has changed. If you take this expression now, right, and do the evaluation, then x is basically steady state, z is steady state. So you put in the value of x and z, which is a and c respectively. And similarly, y and z become b and c respectively. Now we group these terms, so you'll notice that all these are constants, right? So this is a constant and complete. This is a constant complete. This here represents a per unit in terms of change in x, per unit in change in y, and on the other side is a per unit change in z. So next step is to basically make the following approximation that delta z equals dz, delta y equals dy, and delta x equals dx. All right, and so now what we have is a per unit equation. So let's work out an example. We're given the function in implicit form, that is fxyz equals x squared plus y squared minus z equals 0. And we want to compute the percentage change in z at the position 1, 1, 2 if x changes from 2% by 2% and y changes by minus 3%. All right, so we're given it in implicit form, but from previous slides, we know that if we take the partial of f with respect to x, evaluated x equals 1, y equals 1, and z equals 2, this is equivalent to taking the partial of fx in explicit form, evaluated x equals 1, y equals 1, and this value is 2. Similarly, the partial of f with respect to y for the implicit form of the equation ends up being the explicit partial derivative, evaluated x equals 1, y equals 1. And this gives you a value of 2. df dz basically just becomes minus 1 in terms of this expression here. So now we can make the substitutions. These are all numbers now, right? So this here, for instance, it becomes a 2. This one here becomes a 2, right? And so df dx basically times dx over x. dx over x, x over z is, you have x would be 1, and z would be 2. Here it's y over z, so y equals 1, z equals 2. So when you group these two terms together, you'll have basically a 2 coming from here, a 1/2 coming from there, and similarly for the other one. And then you have the dx over x, which is a percentage change in x, which is per unit. dy over y is percentage change in y. And so this term is 1, this term is 1, dx over x is 0.02. and dy over y is 0.03. Put them together and you get minus 0.01. So this is the percentage change in z. All right, let's do a sensitivity analysis example. So you're given that the body mass index BMI for an adult human is given by this function. It's a function of two variables, where W is the weight measured in kilograms and H is the height measured in meters. So the two questions are, first, use differentials dW and dH to approximate the change in the body mass index, dB, when weight increases from 55 to 56.5 kilogram and height increases from 1.65 to 1.66 meters. Second part of the question is, which produces a greater percentage change in the body mass index, a 1% change in the weight at a constant height, or 1% change in the height at a constant weight? All right, so for part A, we basically have to compute the partial derivative of the function b with respect to w and with respect to h. So with respect to w, we end up with 1 over h squared. You can get that directly by taking the partial derivative of this expression here. And that's to be evaluated at 55 and 1.65. If you do that calculation, you get 0.37. Then we have to take the partial derivative with respect to h, again evaluated at the value of 55 and 1.65. In this case, when you take the derivative of this with respect to h, we end up with minus 2w over h cubed. And if we evaluate these results, we get minus 24.49. So now we can write out the differential. dB is just the partial derivative with respect to w, dw, plus the partial derivative with respect to h, dh. dw basically would be just the difference between these two, and the dh would be the difference between these two. So in one case it's 1.5, in the other case it's 0.01. So substitute the numbers in, do the computation, and you get 0.31. Now if we want to do per unit, we would just take this expression and divide both sides by b, which is what I've done here, right? And if you divide through by b, you want to basically eventually divide by w and multiply by w again, which is essentially the step that's taken thereafter. So if we divide through by b, that means that you'd have w over h squared on the denominator, which means the h squared comes on top and the w stays below. So that would be here as well as here. All right, so then you basically make the substitution for bw and bh, which is what we've done here. And then you see you get cancellations taking place. H squared cancels, and you end up with dw over w here. H squared, the w and w cancel, and you get an h squared over h cubed, which means you get an h here. So that's dH over H with a minus 2 here. But if you look at this expression now, this is in per unit form. Right, no units here and no units here. All right, we're given the percentage change for W and the percentage change for H. So we just make the substitution. dW over W is 0.01, whereas dH over H basically is 0.01. So make the substitutions, and we find basically you get a 2% change in B, but it's of the opposite sign. It's minus 0.02. That's after you make the substitutions in, you'll end up with a value of minus 0.02. Anyway, that concludes Lecture 7B. Thank you for listening.